Everybody, and welcome to the class. So we will start by looking at some of the um, things that I gave you to think about in the last class. So I asked you 4 questions. So we first studied about real numbers. We then studied about the properties of real numbers and what can be done in terms of adding, subtracting, or multiplying them. And then we found out there's an identity for multiplication and addition. And then these are the 4 questions that we were left with. Firstly, can pi be represented on the number line? Now this was a very interesting thing because I told you that pi is a real number and I told you that all real numbers can be written on the number line. So the natural question that will come up is, can pi be written on the number line? The answer is yes. Now, how do we write it on the number line? The answer is a little non-intuitive, so you cannot do it with very good accuracy. So the technique that can be used is you could draw a circle with the radius as ½ centimeter. Okay, you could draw a circle with the radius as ½ centimeter, which means its diameter would be 1 centimeter. So the diameter of the circle would be 1 centimeter. So it's 1 centimeter wide and it would be ½ a centimeter in terms of its radius. Then you guys should be knowing of the formula that the circumference of a circle is 2 pi r or the simple method is pi times diameter. That is the way to calculate circumference of any given circle. So we drew a circle with the diameter as 1 centimeter, which means that its circumference would be 1 times pi, correct? So 1 times pi is nothing but pi, because in this case the diameter is just 1. Are you guys understanding what I'm saying? If not, you can please ask questions in the chat. I will. Okay, very good, and thank you for joining, Vishwan. So pi times d is the circumference. So this circle has a circumference of pi, exactly pi. Now, how do we measure the circumference of a circle? We take a thread and we trace the thread along the circumference of the circle. So you start at one point, you keep a thread on one point, and you slowly trace it along the entire circle. Now, this will not probably give you exact accuracy, but it's a way to visualize what may be. And in a perfect situation, in a very perfect universe, if you have extremely efficient tools, it's possible to do it. So what I do is, if this is my circle, so the diameter of the circle is 1 centimeter, right? The diameter is 1 centimeter, and I take a thread and I trace the thread along this circumference. So I keep the thread here and I slowly trace it along the circumference so that I can roughly draw the thread on top of the circle. Now the amount of thread that will be used to cover the entire circle will be pi centimeters, because the circumference of the circle will be pi. Why is the circumference pi? Because its diameter is 1. So then we mark a point on that thread, how much ever we were able to cover with one circle, and we plot it on the number line. But you have to be very careful when plotting it on the number line. The number line should be designed in such a way that each centimeter takes up one number, because the units have to be the same. You cannot just draw a random number line and plot the thread. You should draw a number line where each number is separated by 1 centimeter. So we have 1 centimeter. Okay, just a second, something has gone wrong. Okay. Can you see me now? Sorry. Can others see me? Okay. Maybe Parv, you can try to leave the chat and come back. Okay. So you will draw a number line with 1 centimeter per number, and then you can plot this thread, how much ever you were able to cover on the number line. So you exactly give you 3.1415 whatever centimeters. You will not be able to get an exact measurement of pi, but if the diameter of the circle is 1 centimeter, the circumference has to be pi. That is how the logic works. Okay. So that's the thing. The thing about pi is the ratio of any circumference to its diameter will always be pi. Even if the circle is of diameter 1 centimeter, or if the circle is of diameter trillion centimeters, the ratio of the circumference to the diameter will always be pi. Now, why are we picking 1 centimeter? So that we can get exactly pi as the circumference. If I took 2 centimeters as the diameter of my circle, I would get 2 pi as the circumference. If I took 10 centimeters, I would get 10 pi. And we want exact value of pi. We don't want to again divide the thread into 2 parts or 10 parts. So we take a diameter 1 and then the circumference gives you exactly pi. So the more carefully you trace the circle, you'll get a better value of pi. You can try it by yourself. You can draw a circle. Yes, Lavnish, you can type your question. So you can draw a circle and you can slowly trace a thread along its circumference. It's not that difficult of a job. Yeah, it might not be 100% accurate, but that is the best we can do in terms of understanding what is the value of pi. So you can at least create a hypothetical situation where pi can be plotted on the number line. How is pi calculated? Now that is a very interesting question, and there are many different ways to calculate the actual value of pi, and some of them are beyond the scope of this class. In fact, there was one method which I did not know until 1 week back. So in my math class here, the teacher was talking about it and she gave a way of generating pi. So that was unbelievable. You use some function, you use tan inverse or some things. Yeah. So pi is not a random number. Pi is exactly the circumference divided by the diameter. So if you have a very powerful tool to measure the circumference and divide it by the diameter, you'll get a more and more accurate value of pi. Pi doesn't have any formula. If pi had a formula, it would be a rational number. Remember, a rational number is a number which can be written in this form, p by q. So if pi is irrational, it means that it cannot be written as p by q. It's just a ratio. It's the ratio of the circumference of the circle to the diameter of the circle. And the more accurately you can measure that ratio, the more accurate value of pi you will get. Okay, moving on. I will come back to this later if you have any more questions. Can I add 2 irrational numbers to get a rational number is the question. Yes, Vansh, you can ask your doubt. I will probably reply it after I explain this particular concept. Can I add 2 irrational numbers to get a rational number? This is a very a tricky question, and you can think about it. So what does it mean when we say that we are adding 2 irrational numbers? Can we get 2 irrational numbers to be added in such a way that the answer is a rational number? Interesting. Okay. Well, it seems to be no, but I think there is there is a way by which you can do it. Let's say I want to add wait, let me think. There is a way to do it. I don't recollect at the top of my head, but there is a way to do it using root 2. You can do something. I don't recollect at the top of my head. Just a second, let me look it up. I probably should have done this before the class. I'm sincere apologies for that. Just a second. Okay. So I will give you the answer to that towards the end of the class. We'll think about the next one. The next one is more straightforward. Can I multiply 2 irrational numbers to get a rational number? That is completely possible. I can multiply root 2 and root 2. Both of them are irrational. But if I multiply them together, I will get 2. Correct? I will get 2 as the answer. Now, root 2 times root 2 is 2 because root 2 is defined as the square root of 2. So if you multiply it to itself, you'll obviously get 2. It's like root 16 times root 16 will be 16, right? So root 25 times root 25 is 5 times 5, which will be 25. So in that same logic, if we multiply root 2 to root 2, you'll get 2 as the answer. Okay, so here I have an example to you where we can add 2 irrational numbers and get a rational number. Okay, so suppose one number is 2 plus root 2. I cannot write this in a better way here because I don't have all the tools. And let me say that the other number is 2 minus root 2. Now 2 plus root 2 is irrational because you are adding 2 and root 2. That number will be something like 3 point something something. So you don't know what it is. 2 minus root 2 will also be irrational because root 2 is irrational. So 2 minus root 2 will also be irrational. But when you add these guys together, the root 2's cancel each other out and you get the answer as 4. So this is a way by which I can add two irrational numbers to get a rational number. 2 plus root 2 is irrational. 2 minus root 2 is also irrational. But if I add them together, I get 4. However, the reverse is not true. I cannot add two rational numbers and get an irrational number. That is never possible. That is never possible. If I have one rational number and if I have another rational number, if I add them together, I will never get an irrational number as an answer. Because this number will be something divided by something. The other number will also be something divided by something. So you get two fractions and you can always add them with a common denominator and you will get an answer. So that's why adding two rational numbers will always give rational. But it is possible to add two irrational numbers and get a rational number as the answer. So in this case, you can just do root 3 times root 3, not 2 root 3. Okay. Yeah, so root 8 times root 2 will also be root of 8 times 2, which will be root 16, which is 4. So that is also an example where we can multiply two irrational numbers and get a rational number. Okay, can I divide a rational number by a rational number and get something which is not a rational number? This is a trick question. I asked you this question purposefully, hoping that you would notice where this will not work out. Okay, I am telling you that if I add any two rational numbers, I will always get a rational number because it is p by q. The other one is also p by q. If I multiply two rational numbers, I will always get a rational number because it is p by q multiplied by r over s. You can just multiply the numerators, multiply the denominators. What about division? Can I divide a rational number by another rational number and get something which is not a rational number? Let me say my first rational number is 3. You all know that 3 is a rational number because 3 can be written as 3 divided by 1 or 6 divided by 2. And my other rational number is 0. Now 0 is a rational number. Nobody said that 0 is not a rational number. 0 is an integer, 0 is a whole number, and in some definitions it's also a natural number. So it is definitely a rational number. But if I divide 3 and 0, I will get 3 divided by 0. Now I'm dividing two rational numbers, but the answer is not rational. It's an undefined number. We don't know what it is. We don't know what is 3 divided by 0. So this is the only case. This is the only case where I can divide a rational number by another rational number and get something that is not a rational number. That is if I divide something by 0. In any other situation, if I divide a rational number by another rational number, it's always a, what is that? It's always a rational number. Okay. So one has sent me something. Let me see what it is. He's saying 22 minus root of, I'm not understanding what it is. Maybe you can write it and send it later. Okay, so these are the answers to the things that I asked you to think about. Now, today in this class, we will talk about two things that are extremely important. One is countable infinity and the other is uncountable infinity. Now, before we get into that, I want you to understand what infinity actually means. And recently I was reading my philosophy textbook and I saw some extremely interesting concepts with respect to infinity as to why it is a number that even today people are going to be, spellbounded by. Why it is going to stun them. What is special about it? So infinity is a concept, okay, but we can play with the concept and make it a number. Let me say that I am the manager of a hotel. This is a very famous paradox, by the way. What is the meaning of paradox? Paradox is something where even if it is true, it's a problem, and even if it is false, it's a problem. It's like, for example, I'll give an example of a paradox. Suppose I say that I go and do time travel and I go back 100 years and I kill one of my ancestors. Okay, suppose I don't do this. I'm just giving an example. Suppose I go back in time and I kill my great-great-great-grandfather. Let's say I killed him even before he got married. Okay. Now, how is that possible? Because it creates a paradox. Because if I have gone and killed my great-great-great-grandfather, then I should not be born because I've killed an ancestor and he's responsible for creation of the generations afterwards, right? But I can still go back in time and do whatever I want. So that's a paradoxical situation where either ways there's a problem. So now the hotel infinity. I am a manager of a hotel and let us say that I have infinite rooms in my hotel. It's an endless number of rooms. Let's make it interesting. I said the hotel is located in the middle of the Pacific Ocean, and it has infinite floors upwards. It just keeps going on and on and on. There is in the escalate in the elevator to go up. You just enter whatever number you want to, and you go to your room. Okay, so we stand inside the. We go inside the hotel and we talk to the manager. Okay, so I am the manager. You guys come and talk to me because you say that you want to stay in the hotel. Now the thing is, already I have infinite rooms and all of those rooms has one person in it. So the hotel is full, it's booked. Okay. This is all hypothetical. Don't ask me how it is possible. There are no infinite people in the world. Just a hypothetical situation. I have infinite rooms in my hotel and every room is full. What happens now? You guys come and 6 of you are, you say that we want to stay in the hotel. What do I do? So I tell you, oh, don't worry, it's possible. So what I tell is, I tell everybody to shift to a room that is 6 more than their room. For example, the person in room number 1 goes to room number 7. The person in room number 2 goes to room number 8. Person in room number 10 goes to room number 16. So just 6 more than whatever room they were in. And all the people shift to another room because there are infinite rooms. And now there are rooms 1, 2, 3, 4, 5, 6 which are empty. And the 6 of you are in my hotel. I just moved everybody 6 spaces from where they were originally staying, and now I got 6 rooms vacant. Okay, fine. There's a little. Okay, you guys might say, fine, yeah, we agree. There are infinite rooms, so there are just 6 people that came. So 6 is a very small number when you look at infinity. So you are able to move everybody, and you made it happen. Okay, even though this is questionable, it's almost, let's say, half believable. Now something happens. All of you are happily sitting in the hotel, and suddenly, from another planet, okay, let's say from another planet, infinite number of people come to my hotel. Infinite new people come to my hotel. Okay, so originally I have infinite people. Originally I have infinite people. And now from the other planet, somewhere in the universe, they came to visit my hotel, and infinite more people have come. And they ask me, can we please stay in your hotel? Well, I'm a very nice person. I say, yeah, obviously you can. How? I mean, all the rooms are full. And you cannot even move everybody because there are infinite people. If it is 6 people, yeah, but if there are infinite people, what do you do? What I do is, I tell everybody to go to a room that is double of their room. So 1 goes to 2, 2 goes to 4, 5 goes to 10, and so on. So everybody switches to another room that is double of their room. Now what happens? All the even numbers are occupied because even numbers are all divisible by 2. Remember that. If we double every number, we'll get an even number. So 1 went to 2, 2 went to 4, 3 went to 6, 4 went to 8, 5 went to 10, and all even numbers are occupied. All the odd number rooms are vacant because you cannot multiply something by 2 and get an odd number. You'll always get an even number. So all the even numbers are occupied. All the odd numbers are vacant. And I tell all these people to move into the odd numbers because there are infinite odd numbers. So they move into my hotel. This is very, very strange concept to understand because we initially said that there are infinite people and infinite rooms and all of them are taken. Now I say that Hotel Infinity has a new number of guests, new infinity number of guests. And I say that we can accommodate them by just doing this technique. I tell everybody to go to a room that is double of their room. So all the odd numbers are vacant. That's what happens. Okay. Now, I have a question to you guys. How many people will remain in the hotel after all those aliens leave the hotel? Let's say all those infinite aliens who occupied all my odd numbers, they stayed in my hotel for 5-6 days and then they went back to their planet. Now, how many people are remaining in my hotel?
Infinite.
Infinity. Very good. Because all those even numbers, infinity plus 6, I mean, that's still infinity. Okay, anyway, good. Infinity plus 6 is a good answer, but it's same as infinity. Okay, so how many people left the hotel? infinite people left the hotel, right? Because there were infinite aliens who came, so all of them left. So the infinite people left, and now we have infinite people remaining. So we are saying that initially we had infinite people. Now infinite people left the hotel, and now we have infinite people remaining. Okay, fine, understandable. Now I'll tell you, let us say, let's forget about the alien situation. Let us go back to the previous situation where all the rooms were occupied. When you guys came, I made everybody shift, and you guys took room numbers 1, 2, 3, 4, 5, 6, and everybody else was shifted. Now there are infinite people in the hotel. Suppose all those other people who were there before you came, okay, those other people, let's say all of them leave the hotel, and only you are remaining. Only you guys are remaining. Everybody else leaves. So we had infinite people, and all those infinite people left. Now how many people we have remaining? We have 6 people remaining because you guys are the only ones who are remaining in the hotel. Well, what has happened? In the first situation, infinite people were there, infinite people left, and we still had infinite people. In the second situation, we had infinite people left the hotel, now there are only 6 people. How is that possible? Are you saying that more people left the hotel in the second situation, that's why the quantity got lesser? No, the number of people who left the hotel were same even in the first situation and the second situation. So this creates a paradox. This creates a paradox because the concept of infinity creates these sort of problems. I can also create a situation where I said that all of you were in the hotel, now all of you left the hotel. So infinite people were there, all the infinite people leave the hotel, now there are 0 people remaining. So what is happening here? We are able to remove an infinity from an infinity and be happy with an infinity. We are able to remove an infinity from an infinity and have 6 as our answer. We are able to have infinity removed from infinity and get 0 as the answer. What is happening? That is why I told you, infinity is not exactly a number, it's a concept. You can do all these operations of subtraction, addition with numbers. You cannot do that with a concept, because the concept of infinity says that there are endless number of things. So I cannot technically get rid of all of it. I cannot say, okay, I have infinite people, now all of them left the hotel. That is not technically possible because you cannot subtract anything from that. I cannot say that there are infinite stars in the universe and someday all of them explode. It just doesn't make sense because it's a quantity, it's a definition of something that is endless. So you cannot technically take away something or put something to it and change. In this particular problem, we are able to do that because we have made it into a real life situation. We have created a hypothetical situation where we are saying there's a hotel and there are people and there are rooms. But actually, that is not possible. You cannot do that in reality because it's a concept. It's like saying, suppose I have a time traveling machine and I go trillion years into the future, okay, and I do something in the trillion years in the future, okay, and then I say that if that happened I should have been dead. That doesn't make sense because there is no such thing as going into the future. Same thing with the grandfather paradox. I cannot go back in the past and kill my ancestor and say that, oh, if that happened I should not have been alive. We are mixing reality with concepts, and that creates ambiguity. When you deal with concepts, you should keep it as a concept. Time travel is a concept. You cannot say that, oh, if I do time travel, I'll go and do this. Nobody said that if you do time travel, you can actually go and change the past. Time travel is a concept. It's saying that you can go back in time or you can go forward in time. We are assuming that if we go back in time, I will kill somebody or things like that. That is mixing reality with a concept. So killing somebody, that's a realistic situation. We see that in the world. So we are putting that inside a concept. So that will create ambiguity. So that cannot be done. We should be very careful when we deal with infinities. And the thing about infinity is that it's not always the same. There could be infinities that are small. There could be infinities that are large. What do I mean by that? Well, the infinities that are small can be counted. You can actually list all the things in that infinity. Like for example, the natural numbers are a countable infinity set. Okay, which means I can count the number of natural numbers. I will never reach infinity, but I can still go in that direction. I say 1, 2, 3, 4, 5, 6. I can go on and on and on because I know that there are infinity. It's a countable infinity. However, the set of real numbers is it's an uncountable infinity. We cannot actually count it. It will never be possible for us to list real numbers in some order because it's an uncountable infinity. Let me tell you what happens. Suppose I want to list real numbers between 1 and 2. How will I do it? I'll do okay. I can just keep doing on and on and on here. I will never go beyond this. Then I can say I will do this. And then I can do this. And that can go on and on and on. Then I can say that I will take a number using all the numbers of the previous numbers, the first number, the second number, the third number, the fourth number, the fifth, the sixth, and I'll create a new number. So it's just not a countable infinity. It's uncountable. You can never list it properly. There's just too many of them to count it. So the number of real numbers is more than the number of natural numbers. Even though both of them are infinite, the number of real numbers is more than the number of natural numbers. Okay. So your question is this: is 3 bar infinity? So I say 3, and here I put a bar on top of it. Let me do it like this. Okay, so you're saying, is this infinity? Yes, it's infinity because this is it's a number that you cannot even count. You don't even know what it is. It's just 333. It keeps going on and on and on. It never stops. So it's an infinitely large number. However, if I do 10 by 3, this is not infinity. This is just 3.3333. It's not infinite. It's just a number it's a number between 3 and 4. It's just that we cannot. But however, see, this number can easily be represented as 10 divided by 3. So it's a rational number. Forget about being infinity. It's a rational number. It's not even an irrational number. Guys, don't confuse between a rational number and a number that it goes on and on and on. For example, 3.3333. This number, if it keeps going on and on, it's not irrational. It is still rational because you can write it as 10 divided by 3. However, pi is irrational because you cannot write it as something divided by something. Some fractions exist which don't have proper decimal expansions. They just keep going on and on and on. But that doesn't mean that they are irrational. It just means that they cannot be written down with decimals, but you can still write them with fractions. So any number that can be represented as a fraction, p over q, where p and q are integers, that is always a rational number. Yeah, 10 by 3 is a rational number, and it's non-terminating. So we say non-terminating because the decimal expansion never ends. Okay, now the question is, what is E? Okay, interesting. We'll talk about that some other day because it'll take a lot of time to explain that concept. You can try to Google it on your own, and you can see if you understand what it is. So today we will just talk about infinity and these things. I'll talk about E in the next class. Okay, what is the difference between finite and infinite? It's a good question. Finite is something which we can count, which has a limit, which is not endless, something which ends. Most of the finite numbers can be written as on the number line. You can plot it on the number line. It could be irrational or rational. Now, root 2 is not a rational number, but it is still a finite number because you can plot it on the number line. Okay, so all the numbers that can be plotted on the number line are finite numbers. They have a quantitative value. They are not just concepts. You cannot plot infinity on the number line because how much ever you plot to it will still be a number. I can find another number that is larger than it. So you can never plot a number that is larger than anything else because I can always add 1 to it. Okay, this is the thing about infinity. Now, I could possibly be able to give you actually this example is not correct, but you can try to use it to understand the difference between countable infinities and uncountable infinity. This is actually not a correct example. It's a wrong example, but I just want you to understand the concept. So don't pay too much attention to the example. Just understand the concept. Suppose I want to say which is more, the number of planets in the universe or number of stars in the universe. So the way to do that is I say that I can match every star with another planet. Always. I can match every star with another planet, but there will still be planets remaining. There will still be planets remaining. So I can kind of conclude that the number of planets is almost uncountable, because every time I reach a star, it has so many other planets that I don't know how many are there. It could be 100, 200, whatever it is. And then I say that which is more, the number of stars or the number of moons. So then again, I say that there are so many planets and moons. This is a wrong example, because technically both of them are still countable infinities, because I can even count the number of planets. But I'm giving you this example to show how to differentiate between something that is a small infinity, something that's large. So what happens in the large infinity is I can match every number in the small infinity with something, but I will still have numbers remaining. So that is what happens when I say it's a uncountable infinity. Don't take that example too seriously. I just wanted you to understand the concept, because technically both number of stars and number of planets are equal. They are both countable infinities. So I could always say that I will take away all the stars from their planets. So I will take away all the planets from their stars, and I'll just keep all the planets in a straight line, and I will keep all the stars in a straight line. Then I can say that I will match each planet and every star. So I will never get over with any of them, because both of them are extending in a infinite way, right? So it's not a correct example, but that is the way to think about what is a small infinity and what is a large infinity. Okay, Parv, what is your question? Sir, when we enter a big number in calculator, it shows something E. Okay, that E is different from the small e. Okay, this E is different from the E that you see on the calculator when you multiply something large. That is a way to tell you that it is 1.2 multiplied by 10 to the power something. So that's what it says. So it's actually representing the number in a way, in the short space that it is possible, because the calculator doesn't have room to do more than that. So for example, I did a huge calculation and I got 6.748. I got this, right? I got this. I don't know if you can see it. So what this means, this is 6.748167 multiplied by 10 to the power 9. So there are more numbers here which cannot be represented. So this is what it has done. So suppose I do 1 million times 1 million. I get this. So this is saying it is 1 times 10 to the power 12. And 10 to the power 12 is a trillion. There is no room in the calculator to write that. So it says it is 10 to the power 12. So E talks about 10 to the power how much? Okay. Fine. You're saying it if it is. Oh, no. So why they chose 1.2? Suppose your answer is this. If this is your answer, okay, the way to represent this is by saying this is 1.2 times 10 to the power 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it's 1.2 times 10 to the 14. That is the way to represent this number, because the first two digits are 1, 2. So that is talking about how to represent larger numbers, which if you want I can teach you properly in next class. But so if the number was something like this, then this would be 3.4 multiplied by 10 to the power something. Yeah, it's called a scientific notation. It's an approximation. This is not actually 1.2. It's 1.2994839823948 times 10 to the power 14. But there's no space to write it, so you just approximate and say this is going to be 10 to the power 14. So it's going to be a 15-digit number. And that's the calculator's way of telling us that it's a very big number and you cannot represent it in the calculator. So what happens is the calculator can actually calculate the answer, but it doesn't have space to show the answer. That is the problem. The calculator is a very powerful tool. It can actually do that calculation. So in fact, let me check. So let's see how far this calculator can do the calculation. So suppose I want to do, so I can only type, okay, so let's say I want to do 100 million multiplied by 100 million. So this is saying 10 to the power 16. Now let me say that I want to do 10 to the power 16 times 10 to the power 16. So it's doing 10 to the power 32. Now suppose I do this 10 to the power 64, 10 to the power 128. It is still doing the calculation. It doesn't have space to show it. Then it gives error. So it can still calculate it up to 10 to the power 128. And then it gives an error. So then it goes beyond its ability to even calculate. So then it cannot do it. Some computers can go up to 10 to the power 300. And then depends on the power of the computer. But I'll tell you one thing, guys. any computer in the world, however powerful it is, will not be able to write this number. Okay, think about this. This is what I want you to think about for next class. This number 9 to the power 9 to the power 9. Very important where you put the bracket. This is not the same as this. This is a different number. Sorry, this is a different number. This number can be represented in a big calculator, but we are only talking about the number above that. This is the number which, to write it, you will need kilometers of space. It's a huge number. It's an extremely huge number. And we'll talk about these things in the next class. Okay. Thank you so much, guys. I might have to go now. And if you have any more questions, we'll talk about that in the next class. Okay. Thank you so much. Have a very good Sunday. Bye-bye.